Silicon dioxide.
Silicon dioxide, also known as silica, is a chemical compound that is a dioxide of silicon with the chemical formula CO2. It has been known since ancient times. Silica is most commonly found in nature as quartz, as well as in various living organisms. Silica is one of the most complex and most abundant families of materials, existing both as several minerals and being produced synthetically. Notable examples include fused quartz, crystal, fumed silica, silica gel, and aerogels. Applications range from structural materials to microelectronics to components used in the food industry.
Production.
Silicon dioxide is obtained by mining and purification of the resulting mineral. Quartz comprises more than 10% by mass of the Earth's crust. It is also produced, almost always via the processing of quartz, synthetically on a very large scale.
Fumed silica.
Pyrogenic silica, sometimes called fumed silica or silica fume, is a very fine particulate or colloidal form of silicon dioxide. It is prepared by burning CCl4 in an oxygen-rich hydrocarbon flame to produce a smoke of CO2.
Precipitated silica.
Amorphous silica, silica gel, is produced by the acidification of solutions of sodium silicate. An initially formed gelatinous precipitate is then washed and then dehydrated to produce colorless microporous silica. Idealized equation involving a trisilicate and sulfuric acid is shown. Approximately 1 billion kilograms year, 1999, of silica was produced in this manner, mainly for use for polymer composites, tires and shoe soles.
On microchips.
Thin films of silica grow spontaneously on silicon wafers via thermal oxidation. This route gives a very shallow layer, approximately 1 nanometer or 10A, of so-called native oxide. Higher temperatures and alternative environments are used to grow well-controlled layers of silicon dioxide on silicon, for example at temperatures between 600 and 1200 DEGC, using so-called dry or wet oxidation with O2 or H2O, respectively. The depth of the layer of silicon replaced by the dioxide is 44% of the depth of the silicon dioxide layer produced. The native oxide layer can be beneficial in microelectronics, where it acts as electric insulators with high chemical stability. In electrical applications, it can protect the silicon, store charge, block current, and even act as a controlled pathway to limit current flow.
Laboratory or specialty methods. From silicate esters.
Many routes to silicon dioxide start with silicate esters, the best known being tetrathiol orthosilicate, TEOS. Simply heating TEOS at 680 to 730 DEGC gives the dioxide. Similarly, TEOS combusts around 400 DEGC. TEOS undergoes hydrolysis via the so-called Sol-Gel process. The course of the reaction and nature of the product are affected by catalysts, but the idealized equation is.
Other methods.
Being highly stable, silicon dioxide arises from many methods. Conceptually simple, but of little practical value, combustion of silane gives silicon dioxide. This reaction is analogous to the combustion of methane.
Uses.
An estimated 95% of silicon dioxide produced is consumed in the construction industry, for example for the production of Portland cement. Other major applications are listed below.
Precursor to glass and silicon metal.
Silica is used primarily in the production of glass for windows, drinking glasses, beverage bottles, and many other uses. The majority of optical fibers for telecommunication are also made from silica. It is a primary raw material for many ceramics such as earthenware, stoneware, and porcelain. Silicon dioxide is used to produce elemental silicon. The process involves carbothermic reduction in an electric arc furnace.
Food and pharmaceutical applications.
Silica is a common additive in the production of foods, where it is used primarily as a flow agent in powdered foods, or to absorb water in hygroscopic applications. It is the primary component of diatomaceous earth. Colloidal silica is also used as a wine, beer, and juice thinning agent. In pharmaceutical products, silica aids powder flow when tablets are formed.
Other.
A silica-based aerogel was used in the Stardust spacecraft to collect extraterrestrial particles. Silica is also used in the extraction of DNA and RNA due to its ability to bind to the nucleic acids under the presence of chautrobes. As hydrophobic silica, it is used as a defoamer component. In hydrated form, it is used in toothpaste as a hard abrasive to remove tooth plaque. In its capacity as a refractory, it is useful in fiber form as a high-temperature thermal protection fabric. In cosmetics, it is useful for its light-diffusing properties and natural absorbency. It is also used as a thermal enhancement compound in ground source heat pump industry.
Structure.
In the majority of silicates, the C atom shows tetrahedral coordination, with 4 oxygen atoms surrounding a central C atom. The most common example is seen in the quartz crystalline form of silica CO2. In each of the most thermodynamically stable crystalline forms of silica, on average, all 4 of the vertices, or oxygen atoms, of the CO4 tetrahedra are shared with others, yielding the net chemical formula, CO2. For example, in the unit cell of a quartz, the central tetrahedron shares all 4 of its corner atoms, the 2 face-centered tetrahedra share 2 of their corner atoms, and the 4 edge-centered tetrahedra share just 1 of their atoms with other CO4 tetrahedra. This leaves a net average of 12 out of 24 total vertices for that portion of the 7 CO4 tetrahedra that are considered to be a part of the unit cell for silica, C3d unit cell. CO2 has a number of distinct crystalline forms, polymorphs, in addition to amorphous forms. With the exception of stishovite and fibrous silica, all of the crystalline forms involve tetrahedral CO4 units linked together by shared vertices in different arrangements. Silicon-oxygen bond lengths vary between the different crystal forms. For example, in a quartz the bond length is 161 pm, whereas in a tridymite it is in the range 154 to 171 pm. The COC angle also varies between a low value of 140 deg in a tridymite, up to 180 deg in B tridymite. In a quartz the COC angle is 144 deg. Fibrous silica has a structure similar to that of Cis2 with chains of edge-sharing CO4 tetrahedra. Stishovite, the higher pressure form, in contrast has a rutile-like structure where silicon is 6-coordinate. The density of stishovite is 4.287 grams per centimeter 3, which compares to a quartz, the densest of the low-pressure forms, which has a density of 2.648 grams per centimeter 3. The difference in density can be ascribed to the increase in coordination as the 6 shortest CO bond lengths in stishovite, 4 CO bond lengths of 176 pm and 2 others of 181 pm, are greater than the CO bond length, 161 pm, in a quartz. The change in the coordination increases the ionicity of the CO bond. But more important is the observation that any deviations from these standard parameters constitute microstructural differences or variations, which represent an approach to an amorphous, vitreous or glassy solid. The only stable form under normal conditions is a quartz, and this is the form in which crystalline silicon dioxide is usually encountered. In nature, impurities in crystalline quartz can give rise to colors, see list. The high-temperature minerals, cristobalite and tridymite, have both a lower density and index of refraction than quartz. Since the composition is identical, the reason for the discrepancies must be in the increased spacing in the high-temperature minerals. As is common with many substances, the higher the temperature the farther apart the atoms due to the increased vibration energy. The high-pressure minerals, cyphertite, stishovite, and coesite, on the other hand, have a higher density and index of refraction when compared to quartz. This is probably due to the intense compression of the atoms that must occur during their formation, resulting in a more condensed structure. Phage acid silica is another form of crystalline silica. It is obtained by delumination of a low-sodium, ultra-stable Y-zolite with a combined acid and thermal treatment. The resulting product contains over 99% silica, has high crystallinity and high surface area, over 800 m2 per gram. Phage acid silica has very high thermal and acid stability. For example, it maintains a high degree of long-range molecular order, or crystallinity, even after boiling in concentrated hydrochloric acid. Molten silica exhibits several peculiar physical characteristics that are similar to the ones observed in liquid water: negative temperature expansion, density maximum, at temperatures 5000 degC, and a heat capacity minimum. Its density decreases from 2.08 grams per centimeter 3 at 1950 degC to 2.03 grams per centimeter 3 at 2200 degC. When molecular silicon monoxide, CO, is condensed in an argon matrix cooled with helium along with oxygen atoms generated by microwave discharge, molecular CO2 is produced with a linear structure. Dimeric silicon dioxide, CO2, has been prepared by reacting O2 with matrix-isolated dimeric silicon monoxide, C2O2. In dimeric silicon dioxide there are two oxygen atoms bridging between the silicon atoms with an COC angle of 94 deg and bond length of 164.6 pm, and the terminal CO bond length is 150.2 pm. The CO bond length is 148.3 pm, which compares with the length of 161 pm in a quartz. The bond energy is estimated at 621.7 kJ per mole.
Fused quartz.
When molten silicon dioxide CO2 is rapidly cooled, it does not crystallize but solidifies as a glass. The geometry of the silicon and oxygen centers in glass is similar to that in quartz and most other crystalline forms of the same composition, that is, silicon is surrounded by a regular tetrahedra of oxygen centers. The difference between the glass and the crystalline forms arise from the connectivity of these tetrahedral units. Although there is no long-range periodicity in the glassy network, there remains significant ordering at length scales well beyond the CO bond length. One example of this ordering is found in the preference of the network to form rings of 6 tetrahedra. The glass transition temperature of pure CO2 is about 1475 K.
Chemical reactions.
Silica is converted to silicon by reduction with carbon. Fluorine reacts with silicon dioxide to form CF4NO2, whereas the other halogen gases, Cl2, Br2, I2, are essentially unreactive. Silicon dioxide is attacked by hydrofluoric acid, HF, to produce hexafluorosilicic acid. HF is used to remove all patterned silicon dioxide in the semiconductor industry. Silicon dioxide dissolves in hot concentrated alkali or fused hydroxide, as described in this idealized equation. Silicon dioxide reacts with basic metal oxides, for example sodium oxide, potassium oxide, lead, oxide, zinc oxide, or mixtures of oxides forming silicates and glasses as the COC bonds in silica are broken successively. As an example, a reaction of sodium oxide and CO2 can produce sodium orthosilicate, sodium silicate, and glasses, dependent on the proportions of reactants. Examples of such glasses have commercial significance, for example soda-lime glass, borosilicate glass, lead glass. In these glasses, silica is termed the network former or lattice former. Silicon dioxide reacts with elemental silicon at high temperatures to produce CO.
Solubility in water.
The solubility of silicon dioxide in water strongly depends on its crystalline form and is 3 to 4 times higher for silica than quartz. As a function of temperature, it peaks at about 340 degC. This property is used to grow single crystals of quartz in a hydrothermal process where natural quartz is dissolved in superheated water in a pressure vessel that is cooler at the top. Crystals of 0.5 to 1 kg can be grown over a period of 1 to 2 months. These crystals are a source of very pure quartz for use in electronic applications.
Occurrence. Biology.
Even though it is poorly soluble, silica occurs widely in many plants. Plant materials with high silica phytolith content appear to be of importance to grazing animals, from chewing insects to ungulates. Studies have shown that it accelerates tooth wear, and high levels of silica in plants frequently eaten by herbivores may have developed as a defense mechanism against predation. It is also the primary component of rice husk ash, which is used, for example, in filtration and cement manufacturing. Silicification in and by cells has been common in the biological world for well over a billion years. In the modern world it occurs in bacteria, single-celled organisms, plants, and animals, invertebrates and vertebrates. Prominent examples include tests or fustules of diatoms and radiolaria, silica phytoliths in the cells of many plants, including Equisetaceae, practically all grasses, and a wide range of dicotyledons, the spicules forming the skeleton of many sponges. Crystalline minerals formed in the physiological environment often show exceptional physical properties, for example strength, hardness, fracture toughness, and tend to form hierarchical structures that exhibit microstructural order over a range of scales. The minerals are crystallized from an environment that is undersaturated with respect to silicon, and under conditions of neutral pH and low temperature, 0 to 40 degC. Formation of the mineral may occur either within the cell wall of an organism, such as with phytoliths, or outside the cell wall, as typically happens with tests. Specific biochemical reactions exist for mineral deposition. Such reactions include those that involve lipids, proteins, and carbohydrates. It is unclear in what ways silica is important in the nutrition of animal. This field of research is challenging because silica is ubiquitous and in most circumstances dissolves in trace quantities only. All the same, it certainly does occur in the living body, leaving us with the problem that it is hard to create proper silica-free controls for purposes of research. This makes it difficult to be sure when the silica present has had operative beneficial effects, and when its presence is coincidental, or even harmful. The current consensus is that it certainly seems important in the growth, strength, and management of many connective tissues. This is true not only for hard connective tissues such as bone and tooth but possibly in the biochemistry of the subcellular enzyme-containing structures as well.
Health effects.
Silica ingested orally is essentially non-toxic, with an LD50 of 5,000 mg per kilogram. On the other hand, inhaling finely divided crystalline silica dust can lead to silicosis, bronchitis, or cancer, as the dust becomes lodged in the lungs and continuously irritates them, reducing lung capacities. Prior to new rules issued in 2013, OSHA allowed 100 micrograms a cubic meter of air. The new regulations reduced the amount of 50 Ug-M3 down from 100 Ug-M3. The exposure limit for the construction industry is also set at 50 Ug-M3 down from 250 Ug-M3. In the body, crystalline silica particles do not dissolve over clinically relevant periods. Silica crystals can activate the NLRP3 inflammasome inside macrophages and dendritic cells and thereby result in processing of pro-interleukin-1 beta into its mature form. Chronic exposure to silica may thereby account for some of its health hazards, as interleukin-1 is a highly pro-inflammatory cytokine in the immune system. This effect can create an occupational hazard for people working with sandblasting equipment, products that contain powdered crystalline silica and so on. Children, asthmatics of any age, allergy sufferers, and the elderly, all of whom have reduced lung capacity, can be affected in much less time. Amorphous silica, such as fumed silica, is not associated with development of silicosis, but may cause irreversible lung damage in some cases. Laws restricting silica exposure with respect to the silicosis hazard specify that they are concerned only with silica that is both crystalline and dust-forming. A study that followed subjects for 15 years found that higher levels of silica in water appeared to decrease the risk of dementia. The study found an association between an increase of 10 mg per day of the intake of silica in drinking water with a decreased risk of dementia of 11%. Crystalline silica is used in hydraulic fracturing of formation which contain tight oil and shale gas, a use which presents a health hazard to workers. In 2013 OSHA announced tightened restrictions on the amount of crystalline silica which could be present and required green completion of fracked wells to reduce exposure during the initial burst of material emitted by a fracked well.
Crystalline forms of silicon dioxide.
CO2, more so than almost any material, exists in many crystalline forms, called polymorphs,